Hi everyone, I'm Shouqian from UC Santa Cruz. I will present our paper, Concurrent Entanglement Routing for Quantum Networks, Model and Designs. It's a joint work with Professor Chen Qian at UC Santa Cruz. Let's start with the fundamental building block for the quantum network, quantum entanglements. A quantum entanglement is a state correlation of two particles, or called qubits, like the spin direction of the electrons. Let's forget about the electrons. To make it available to the majority of the SIGCOMM audience, we hide the physical details and show the key idea of the quantum entanglement. You can instead think of quantum entanglement as two flipping coins, and they are correlated such that even if we have no idea what the result will be for the two coins, we can stop one coin to get a result for both. Suppose we stop this one and we get 1. Since the two coins are correlated, this one here is no longer random to us. Besides, the entanglement is preserved even if they are separated by a large distance. Suppose we make two coins entangled and separate them, they will still show the same result. To illustrate the establishment of entanglement, we use the big blue circles to denote the communication parties, Alice and Bob, and the small red dots for the qubits, like the coins. Alice and Bob send photons via a quantum channel. For example, the optical fiber, denoted as a dashed line here. Then, a quantum entanglement can be established by sending a single photon from each party. And as the success rate for a single try is low, multiple tries are typically performed to get entanglement. This process is detailed in the link layer paper SIGCOMM last year. Quantum entanglement enables perfectly secure data transmission. This is achieved with the help of classical communication, where authenticity and integrity are assumed, but confidentiality flaws potentially exist. Suppose you and your friend share a pair of entangled coins, and the coins show 0 at your place. Automatically, the other end must also show 0. If you want to send the bit 0 perfectly securely, it's easy by saying, hey, you got the coin bit? Don't tell others, and let me tell you, the 1-bit data I want to send to you is the same as the coin shows. Vice versa. The confidentiality is perfectly preserved even if the same or opposite information is sent in public. A more complicated version is also available to teleport the quantum state of a particle, called quantum teleportation. Besides, remote quantum key distribution and other applications are enabled by the quantum entanglement. To establish an entanglement for a remote pair of parties, we can use the previous way by sending photons over a long optical fiber. But the problem is, the success rate decreases exponentially with the distance the photons travel. In other words, exponentially more tries should be performed to have a decent success rate. To mitigate the exponential degradation, we can use multiple channels and try entanglements in parallel. Also, we can put relays along the path. The relays are called repeaters. The workflow of building an entanglement via repeaters is as follows. First, local entanglements are built over the optical fiber. Then, each repeater performs a Bell state measurement, or BSM, between its two qubits locally, illustrated in the bold solid line. The repeater needs to inform Alice and Bob about the result of the BSM via classical information. This message is typically 2 bits in length. After that, Alice and Bob share a 2-hop entanglement. This workflow is transitive, which enables building entanglements more hops away. 2 major limitations present in the quantum network. First, the preservation time for an established entanglement is as short as seconds. Hence, the hop-by-hop routing that works well in classical network is hard to apply. We adopt a synchronized communication model which has a slotted and phased timeline. Any routing succeeds or fails in a single slot, and no states are preserved across time slots. Each time slot is further divided into 4 phases to synchronize. The second limitation is the hardware resource contention, including the number of qubits in a quantum computer and the number of quantum channels on a node connecting its neighbors. The two unique types of resources are both limited in number and allocated exclusively in a time slot. We use the following animation to demonstrate the slotted communication model and the resource contentions. Let's consider the quantum network model. First, we have a number of nodes. Each node is equipped with a classical computer and a quantum computer, and thus it has classical and quantum processing power at the same time. All nodes have access to the internet and can communicate with each other on the classical computer part, with potential confidentiality flaws. And we assume the integrity of the classical communication. We use the dashed line to denote a quantum channel. The nodes are connected with the quantum channels to form the quantum part of the network. You may notice that more than one channels may present among the same pair of nodes, and hence, multiple entanglements may be established simultaneously. To establish a local entanglement, each end of the channel should be assigned with a qubit, as the legend shows. And the local entanglement is shown as a solid line between the qubits. The quantum processing power of a node is determined by the number of qubits it holds in a quantum computer. For example, with 3 qubits in node 9, it can simultaneously establish 3 entanglements with its neighbors. As there are more than 3 channels connecting the outside, the qubits are properly assigned up to 3 channels, 1 qubit per channel. As a pair of neighbors may share multiple parallel channels, like node 7 and node 9, multiple pairs of qubits can be assigned to the parallel channels. Let's move on to the communication model by following the workflow of a single time slot with 4 phases. In phase 1, from pure classical communication, each node is informed of a list for the node pairs to build a multi-hop entanglement. In this example, a single pair, node 3 and node 11. In phase 2, each node exclusively assigns its qubits to quantum channels connecting it. This assignment is based on a consistent path selection across different nodes. For example, the highlighted 2 paths are selected. Then, the qubits are assigned to the channels to fulfill the path. After the assignment, each node tries entanglement on the selected channels until a success or a timeout. In phase 3, each node knows the entanglement results and exchanges this information within k-hop, such that each node has a k-hop view of the entanglement successfulness for the selected channels. We call this k-hop link state. In this example, the channels 3.7 and 9.12 fail, while 3.9, 9.7, 7.11 succeed. The parameter k is determined by the classical network speed and entanglement decay time. Typically, 3 is enough according to our experiments. Finally, in phase 4, each node do the biostate measurement based on its k-hop link states, like the bold solid lines shown in node 7 and node 9. Then, the measurement results are sent to node 3 and node 11 to help them adjust their qubits for a remote entanglement. So far, based on our network and communication model, the multiple entanglement delivery is equivalent to the routing problem in a special network topology, with limitations on time and resources. We claim the following key differences for routing in quantum networks versus that in the classical ones. First, the slotted time prevents the hop-by-hop routing because we cannot retry a field entanglement as retransmitting a field packet in classical networks. Second, the assignments or bindings are fixed in a time slot, including the assignments from qubits to channels and the pairs of qubits to perform biostate measurements. Third, the link states are both static and dynamic because the network topology, including the nodes, channels, and qubits, and their interconnections, is rather stable and is publicly known by all nodes. This guarantees all nodes agree on the same path selection and perform consistent qubit assignments in phase 2. However, the entanglement on each quantum channel succeeds probabilistically, not predicted by any means. This requires a link state sharing among neighbors in phase 3 and do BSMs accordingly in phase 4. The fourth difference is that the routing metric for a path is non-additive, due to the presence of parallel channels and the flexible choices for biostate measurements in phase 4. The routing metric is a quantitative evaluation of a path with which we can compare two paths. We show the non-additivity in the next slide. In view of the above differences, the existing routing algorithms in packet switching, circuit switching, and wireless networks may not directly apply. Let's explore the non-additive routing metric. When the paths do not overlap, things are simple and straightforward. As shown in Figure A, there are two separate paths connecting nodes A and B, and unfortunately, both paths fail because they both have a failed channel. However, things become interesting when paths overlap. Figure B shows two fully overlapped paths connecting A and B, and after phase 2, nodes find out that 3 links fail. But still, nodes C and D manage to find a valid path by switching back and forth between the two parallel paths. We identify paths in quantum networks by width and hops. For example, the path ACDB has 2 channels each hop, 3 hops in total, and is denoted as a 2-3 path. We derive formulas for general scenarios, and the routing cost turns out non-additive when the path grows by 1 hop. Please refer to our paper for details. Intuitively, we prefer wider paths during routing. The goal of our proposed routing algorithm is to deliver the maximum number of entanglements based on the network and communication model. Or we can say, to maximize the throughput. Toward this goal, we propose 2 algorithms. QPath pre-calculates multiple contention-free paths for all 2 node combinations and selects a path at runtime. It repairs failed channels in a segment-based style. Due to time limit, please refer to our paper for more details. QCast overcomes some shortcomings of the QPath and finds paths at runtime for better flexibility. It recovers from failed channels by an exclusive OR-based algorithm. We will focus on QCast. QCast is short for quantum contention-free path selection at runtime. The word contention-free means paths do not share any qubit or channel. For example, in this figure, 2 paths present between A and B, ACB and ADEB. They don't share any qubit or channel, and thus they are contention-free. Due to contention, DC and the second channel for CB are not allowed. QCast extends the Dijkstra algorithm to select a contention-free path under non-additive metric. This intention works for all monotonic metrics, and we did several optimizations for the specific metric. Please refer to our paper for details. Monotonic here means when adding 1 hop to a path, it's always getting worse. Like in this example, we have the path AC, and when we add CB, the path ACB always evaluates worse than AC. The workflow of QCast is as following. In phase 1, nodes are informed to build entanglements between node 4 and node 14, and node 3 and node 11. In phase 2, local entanglements are built based on the contention-free routing. First, for each source and destination pair, the best path is found as a candidate, allowing contentions. The 2 paths are shown in green. Then, the path with the best metric among all the candidate paths is picked. Here, the path 4, 6, 14. And other paths remain in the pending state. The qubits and channels are allocated for the picked path, preventing resource contention with the following paths, which are not as good according to our metric and our algorithm. The selecting and occupying repeat until no more paths are available. These paths are called major paths. After major paths, partial paths are found and allocated with resources to recover from entanglement fields for previously selected major paths, as shown in black. Please refer to our paper for the algorithm to select partial paths. In phase 3, nodes know their local link states within K-hop. Then, each node performs biostate measurement to connect the successful path. Due to the recovery algorithm, links 5-8 and 12-11 are fixed by the partial path. We detail the recovery algorithm in the next slide. Suppose this network topology in resource assignment for node pair A and B. We have a major path A, C, D, E, B. AFE is a partial path, which forms a loop with the part of the major path to repair the link failure in AC, CD, or DE. Also, DGHB is another partial path to recover DE or EB. The interesting things happen when CD and EB both fail. First, AFB is used for the repair. The current path is a major path, ACDEB. The new path is updated from the exclusive OR of the blue major path and the green loop, AFEDCA. The exclusive OR of the two paths is defined as deleting the channels that appears in both paths. In this example, after applying the exclusive OR, the current path is AFEB. Similarly, to repair EB, the black loop is applied to the current path via exclusive OR. The resulting path looks like this, successfully bypassing all the failed channels. Finally, the path between A and B is repaired. For evaluation, we implement QPath and QCast and compare them with two more algorithms, Greedy and SLMP. We evaluate the algorithms on throughput and see how path recovery algorithms contribute to throughput. The network topology is generated from many parameters, and we set forth a reference setting and change one parameter at a time to reduce the parameter scan space to a decent one. A graphical interface is developed to monitor the routing process. This figure shows the cumulative distribution function of throughput for QPath, QCast, Greedy, and SLMP under the reference setting. The throughput results are calculated in terms of entangled base per time slot, or EPS. QCast shows great advantages over other algorithms and outperforms the QPath about 4 EPS. QCast is also the most reliable because it seldom delivers less than 5 EPS. If we lower the entanglement success rate from 0.6 to 0.3, all algorithms degrade like this. SLMP seldom delivers an entanglement. If we enlarge the network size from 100 nodes to 400 nodes, the throughput degrades about 30%. In phase 3, each node shares its link states with its k-hop neighbors, and hence k influences the path recovery performance. The infinity here means all link states are known by all nodes in phase 3 in our simulation. K contributes little to the overall performance because most path failures are just one hop, which can be recovered with local link states. Setting K to 3 is sufficient for QCast. We evaluate the scalability of the routing algorithms with the size of the network N. A larger network means the average distance of the SD pair is longer, and all the algorithms exhibit a logarithmic throughput degrees with the network size. We evaluate the scalability of the routing algorithms with a number of concurrent source and destination pairs. Due to resource contentions, all algorithms scale sublinearly. We evaluate the contribution of recovery paths to the overall throughput for both QPath and QCast by comparing their throughput with that of their recovery path-free versions. With path recovery, the QPath performs slightly better, while QCast enjoys a larger improvement, about 1 entanglement per time slot. As a conclusion, we introduced a quantum network model and associated communication model for routing entanglements. The model shows its differences from classical network, the slotted time, the probabilistic link states, and the non-additive routing metric. We propose two algorithms based on the network model. QPath focuses on calculating contention-free paths offline, while QCast finds paths with better flexibility at runtime. We believe much more smart algorithms for routing entanglements are on their way, and more optimization goals can be taken into consideration, such as better fairness and better quality of service. If you're interested in more details, please feel free to read our paper and contact us via email. Please feel free to try our implementation of QPassing and QCast on this link. Thank you for listening. Any questions?